Hello, this is Justin Schaper, and this is my final project presentation for ADTA 5560 recurrent neural networks. First section is, of course, talking about our time series data set. I had a little bit of a personal interest in this one. I'm probably one of the older students in the class, and my first attempt at actually undergraduate back in the 80s was at the University of Colorado in Boulder. And there I had the opportunity to have probably what was at the time one of the world's coolest work study jobs with the National Oceanographic and Atmospheric Association and their Space Environment Lab, which included measurements of solar activity, forecasting, and geomagnetic observations and data. I got to work with a lot of neat things there, but it got me interested in the topic of basically space weather, if you will. And that led me to the idea for this project of looking at sunspot data. I did a little bit of research, actually starting from the NOAA website, which took me to the Royal Observatory of Belgium's website, and specifically their Solar Influences Data Analysis Center. This center is the archive keeper of even the old manual observations going all the way back to 1749 of sunspot activity. Sunspots are measured just by visual observation, literally counting the spots on the sun and doing that in a consistent way. And that's been going on now for over 250 years. And the Royal Observatory of Belgium, again, they're the keeper of the records there. So they have made all this data, wonderful data, available for download. I found a specific data set that was monthly averages for, again, this 200 and almost 50-year period. That for me had meant that I had just a little under 3,300 data points for use on training and testing, and then the most recent 5 years of data, 60 months, that I held out for forecasting. I should point out that solar activity has a well-known 11-year activity cycle that is like clockwork, and that becomes a relevant factor in some of the modeling considerations that I'll talk about a little later on in the presentation. If anyone's interested in this, I would definitely encourage. It's super easy to find the data. The link there is on the slide, of course, available in CSV files that are very readily consumed, and good explanations about the background and the measurement. As part of the EDA, though, exploratory data analysis, here's a view of what the last 200 and some odd years looks like on sunspot activity. So the data point on the left is January of 1749. The data point on the right is January of 2023. I mentioned the 11-year cycle. You can see that peak to peak to peak, if we had the time axis down there, these are occurring very regularly on 11-year periodicity. So this is the data set we're working with. And as we get into part 3, I'll go a little bit more into how some of these cyclical features became relevant in the model design. But now, moving on to part 2 and simple RNNs and the exercise with generated sine wave data. One of the observations I had from the homework assignment where we did this previously was that I felt like the models could have used from a longer data training run. So one of the things I intentionally changed at the beginning was to generate a longer sequence of sine wave data. I had over 4,000 data points, which captures 40 plus phases or cycles within that. I landed on 85 neurons, but I did experiment with ranges going from 50 neurons on one end all the way up to 100. I did find that the input data sequence length of 50, which I think was one of our defaults earlier, performed well. Most of the experimentation, though, that I had a chance to do at this part of the project was really around the number of neurons. I found that really interesting. One of the things I also found was that I wanted to play around with training epochs maybe a little bit more than was practical. So one of the other methods I wanted to highlight was the Keras TensorFlow early stopping method, which if you set that in place, allows you to condition parameters so that you won't just endlessly go through epochs if you set a high value. So for example, I might have set one with 100 epochs on it, but with the early stopping in place, I would say if you get to a certain MSC or loss point, go ahead and stop at that point. It also allows you to say, okay, I want to wait for 3 more iterations before I stop or whatever. But it allows you to manage that so you can get a little bit more loose on how many epochs you go, and definitely one I think worth looking up. With this particular model, the simple RNN, I ended up with a loss MSE of under 0.001, a very, very tight fit, as you'll see coming up. So this is the visualization of that model. Again, 85 neurons of actual in blue in the generated sine wave data, and then the orange being the predicted value. You can see, especially the first few cycles, pretty tight fit, although a little bit of consistent divergence away from the max peaks. In fact, you can see that growing a little over time, and you can see it's creeping a little bit out of phase as we go. I did find that with 85 neurons, I actually tried running it a few different times and found that between some of the random nature and the time series generator and how the sampling is done, and I'm sure also with some of the random initialization parameters on the weights and biases, that I could have exactly the same neural structure and get slightly different results, although they tended to be close. I actually had one other run that was an even better fit than this one, but failed to save it off. And so all I had was the screenshot. But that was another thing I think I learned out of this project, was that once you feel like you got the right idea on an architecture, not a bad idea to try and run it through a few times just to see if the results tend to be unstable or if they seem to be consistent. I mentioned those differences and how they seem to be sort of growing over each cycle. I thought that was interesting. Obviously, it would suggest that this sort of model you wouldn't be using for like a long-range simulator of a sine wave generator or for longer range forecasting. I did find that there was one other setting configuration I'd used that I found gave an idea to me in terms of how to address a problem like that. So this I found to be an interesting failure. I ran this at 100 neurons, all the other settings the same. And what I got out was basically a square wave step function. So again, that's an orange, the generated model, the blue is the actual. What you can see in this, though, is that the max peak is pretty close to the same place. It's got some stability, some consistency over time. Same with the minimum peak. And then actually the phasing, if you look at where the orange intersects the blue, you can see that the phasing is pretty close. It's not exactly there, but it's really close. This led me to an idea I hadn't considered outside of the class previously, which is using additional pre-processing techniques on a neural network. I didn't implement that here, but it does seem like for further exploration, one of the things you could do is take a model like this and then do some transforms on the output by doing like an offset that would lower a scaling function that would then line up the min and max, and then some shaping functions to get it closer to the sine wave if you wanted. But the idea just of having a neural network that then there's some post-processing math done on to get a better model fit, to me, that was a new concept, and I was glad that the project kind of introduced that idea to me. Okay, now part three, really the LSTM homework types of problems. I won't go into too much detail because I feel like all of us probably know this pretty well now through Dr. Nguyen's lectures. And I'm sure we've all spent a lot of time on this one. But with the vanishing gradient problem, to briefly define it, this is something that comes up during the back propagation part of training. So when you're doing a gradient calculation, that is the differential of the error to the differential of the weights or biases, and you're doing that across multiple, and then you're bringing that back multiple layers, it is effectively just a multiplication problem of small numbers. And so as those gradients get smaller, as your learning rate gets smaller, those numbers have less and less of an effect on early weights that occur farther back in the sequence of the layers. So this effectively is creating a memory problem in that what is happening most recently dominates the learning experience of the model, but what happened far previously tends to get lost through the vanishing gradient, or under the right conditions, an exploding gradient where things would go the other way. With the LSTM architecture, though, by having the cell state channel and gates that control or manage the flow of that cell state channel, you actually have the opportunity to do unhindered backflow of the gradient. So back propagation has the opportunity to occur without the vanishing problem. And part of that is just eliminating the multiplication of the multiple differentiations, excuse me. And so that means, though, that you now have the ability to retain information and signal from earlier layers, effectively creating a longer-term memory solution. The forget gate within the gates of that, also at the same time, they'll give you the ability to train a network to forget something after a certain point in time as well. So that allows you to train it so that something that happened far enough back does not have the impact. Now, for me, that became relevant when thinking about the sunspot data, because, again, 3,300 data points isn't really a lot. But as I think about the cycles and I think about how many periods are in a full cycle, it made me realize that, yeah, I really, what is happening now is very much a factor of things that maybe happened multiple years previously. And then that impact of those multiple years has future effect as well. So that to me suggested that the LSTM architecture, that neural model approach, would be effective in doing this kind of modeling. I should say, I mentioned I worked back at the Space Environment Lab back in the day. The sort of modeling and forecasting we did then was very different. It tended to rely on things like fast Fourier transforms, linear regression analysis, some multi-regression analysis. We did get into some simulations, but neural nets were not on the list. So this was a great opportunity to actually come back and revisit something with a new tool. I wish we'd had it then. So now moving into part 4, the actual modeling, LSTM with time series data. This is my design. The architecture that I used here is actually similar, identical at this level to what we'd used in the homework project. So this has 3 LSTM layers, each with 50 neurons, and then 2 dropout layers in between, each with 20% dropout. I'll go ahead and spoiler alert, my next iteration on this uses the same architecture. What I ended up adjusting was in a different area of the parameters, not the architecture itself. So then these, of course, then feed into a single neuron dense feed-forward neural network to get the final output. So again, architecture, same as what we've seen before. Now, here are the build parameters that I used. So training and test split was again at 90% and 10%. Again, 3 LSTM layers with 50 neurons each, 2 dropout layers with 20% dropout percent. My initial run was with a length on the input sequence of 60 data points. I'll tell you right now that I did end up changing that in the next iteration, but for now I started at 60. Batch size, as we've used before, at 32, optimizer on Atom, loss function MSE. For this first run, I used 50 training epochs. I did not use the early stopping function because I wanted to just have a little more manual control as I was doing this. But then periods to forecast, again, I did a 5-year holdout or 60 data point holdout for the forecasting. And this is what the loss function looks like during the training phase on the first model. Again, 50 epochs, good quick drop down, the elbow curve experience. So this seems to be that the training is effective and not producing anything anomalous. The loss was 0.0046, which out of the different iterations, this was actually a really good loss value. So pretty happy with this as the first run out of the gate. Interesting conversation that we get to the second model on that one. This is the view on testing. So the prediction is in orange, the blue is the actual sunspot activity. You can see it's capturing the cycle really nicely. The minimums aren't too far off, but the maximum peaks are pretty far off. And this is really where the bulk of the loss function is coming from, is being that far away from the peaks. I will point out that that was true, especially in the first one and in the second one, a little less so in the third one. We'll have an interesting comparison here to the second model, though, coming up. When looked at from a forecasting point of view, taking in the holdout data and running that through the model, we got good connectivity back to the data set. So being a Python relative newbie, I was pleased to see that that worked, and I didn't screw up the data processing and the joining of the forecast data to the actual. So visually, that's telling me I got that right. Looking at the pattern, the characteristic here would be consistent and not out of expectation. It seems like we're, looking into a new 11-year peak here. So that would sort of make sense until we realize it's not quite been 11 years since the last peak. But just on the face value, the forecast doesn't seem unreasonable until you look at a little more closer versus the actual for these last 5 years. So over the last 5 years now, loaded in blue, so a 60-month period, There's my model. I can see that I started out not too far off, but actually rapidly diverged, especially at about 1 year out, about 12 months out. I get a big divergence from the actual versus the model. I also get this inflection point about 3 years into it that you just don't see that here in the data. It might be coming down closer, but they're going the wrong way. If I were looking for something to deploy into production, probably not the model I would choose, even with the low MSC. So now we'll move to the redesign. I've dropped a few hints here and there of the pieces that I thought to try. And a lot of that had to do with the cycle time and the length of the inherent 11-year cycle. So this to me was poor performance on the initial model. I was not happy with that. The input sequence length, though, was what got my attention first. So I started in the initial model with 50 data points as the input sequence, which means that on an 11-year cycle, the model, the network, is only seeing less than half of a cycle at one time. Now, between sampling and how the window slides as that goes, it eventually sees all the cycles, which is how we're getting the fit as well as we are, but it is not really getting the whole picture to work on at one time. So with that 11-year cycle, that's 132 data points to encompass to get the full picture. By looking at a 12-month by 11-year by 5 cycles, being able to see 5 complete cycles at a time, I'm looking at a pretty long sequence there, 660 data points. But that to me seemed to be a reasonable next iteration to try to see if we could solve some of that problem with the forecasting. So with that in place, here's the new build parameters as I use them for this. Again, everything not in red was the same as in the first version. So the 90-10 training test split, the architecture was the same with 3 LSTM layers, 50 neurons in each layer, 2 dropouts, 20%. But here is my much longer revised input sequence. Same batch size, still using Atom, MSE. I did lower the training epochs. Mostly I was concerned with that longer input sequence. I'd probably burn a little bit longer on training time. And although it was longer, it wasn't as bad as I was expecting, but I manually set training epochs to 5. I probably could have taken that out a little further. And if I were to go back and redo it, I would almost certainly run that back at 50 as I'd done on the prior model. Again, those same forecasting period that I'm looking at, 60 months or 5 years. So here's the training results, looking again at the loss function. Again, only went out to 5 epochs. Here's the MSE. We get still that elbow curve, so I felt like the training was effective. We leveled off pretty quickly between the 4th or index 3 and 5th or index 4 epochs. Relatively flat. There might have been even a little bump up, but the MSE, the loss function, was 0.0067. Now, you might recall that's a little bit higher than the loss on the first one. And so just superficially, if all I was looking at was the MSE, I would lean towards the first model over this one. But I don't think for the likely use cases of a model like this, that would be appropriate. I think there'd be other features to take into account, and I'll talk a little bit about those here in a moment when I do the side-by-side comparison. So with the revised model, here's what it looked like coming out of testing. Again, the orange is the predicted model, the model predictions. The blue is the actual. Again, I got good fit on the cycles. Peaks and valleys are happening where we would expect them to. The low parts, the minimums, are occurring closer now than they were before. Still off on the maximums, though. And what MSC's there tends to really be coming from that first and second one, although I would point out the third one, I seem to be a little bit closer. And again, a side-by-side would make that a little more evident there. Again, though, not a bad fit overall. Still a little concern over the high peaks there. Then just again, the forecasting and the forecast join to sort of the visual QA. This, though, it's kind of evident from this one that now I'm no longer suggesting that we're right at a peak or coming off of a peak, as the first forecast does. This really shows we're still coming up on one, but have not hit it yet. In fact, that's a little more evident when we zoom in and look at the forecast versus actual for the last 5 years. And here's the sunspot actual in blue again, and the model output in orange. Really pleased to see it starting here, kind of dead middle of where actuals are. And although it does deviate a little bit, it largely is following the curve of the actual. So we've got a better fit in that regard. If I were to forecast this out another 5 years, I'm less confident that it would be as good as a fit. You can see in the actual, we're still climbing higher quite a bit quickly. The model shows it's starting to inflect over a little bit, but not turning all the way around yet. So I should point out, for those of you who have the interest, we are in fact coming up toward a new peak in the 11-year cycle, but are not there yet, and certainly the actual data would support that. So that was off of the second iteration of the model, and again, really the only thing I changed, I left the architecture the same, but changed the data input sequence to something that would give the model a bigger view of past history. And then again, coming back to the earlier thesis, that past history, and this is where again the LSTM differences by being able to hold that longer memory really come into play, because what happened 5 cycles ago, 55 years ago, is actually of relevance when it comes to predicting what's going on now. Okay, now the model performance sort of side-by-side comparison. I had multiple other graphs, but I felt like it really all came down to these two. So this is just simply looking at the forecast performance. The one on the left is from the first version. Again, you see we had the big deviation and the weird inflection point, or the premature inflection point there. And then the second one from the second model, better fit. I will apologize, I forgot to rescale these when I brought them in for the side-by-side. So this is on a lower scale, 0 to 140. That again being the actual sunspot count, the number of spots on the sun. And then this one is at a scale of 200 because the model went so much higher. But again, this was, I think, a lesson learned even, is that just strictly looking at the loss calculation between these two models, I would not have guessed that this was the lower loss function for the model itself overall versus this one. Now, again, that loss function is not calculated on the forecast data, it's calculated on the model and the training. But that to me does demonstrate the idea that just looking at the loss numbers, whatever metric you're looking at there, is not by itself the full picture. You really do have to look at how does the model fit the data characteristics overall. And in this context of using this as a forecast tool, I would certainly not want to use this model. I would be more inclined to lean into this one, which seems to have a better look ahead than the other. Okay, learnings and experiences. First thing I will say is that it still surprises me, having worked with other kinds of predictive models before, and again, starting from more things like linear regression, multivariate linear regression, and fast Fourier transform signal processing stuff. It surprises me how much network builds can give you just very different results, even with minimal changes. Coming back to the early sine wave part of the exercise, just changing or adding 1 or 2 neurons would have such a big impact on the output. I found that very surprising and very telling. The other thing I mentioned, I think at the time, was that reruns of the exact same build can result in different models, different output. Part of this is the sampling and the time series generation, but also part of it is that sort of random initialization on the weights and biases when the network first starts training. To me, that really stresses the importance of building models multiple times, training on multiple different data sets, and looking for some stability in the final output, as opposed to just looking for a good fit. I think the next thing I would mention is that when you're looking at your data, naturally present cycles and relationships from longitudinal data to more current data, you should be mindful of that in terms of how that impacts your sequence input length. In my example, the sunspot activity, and starting with 50 and then ended up at 660, I wouldn't have gotten there if I was just iterating, but by being thoughtful about the length of the natural cycle and some of the physics and how that all plays out, led me to something that worked, I thought, really well early on, without having to go through some of the different experiments I went through, for example, in the sine wave part of the project. And then that also led me to a thought that I briefly mentioned earlier, is that some models might lend themselves to additional post-processing. The sine wave and sort of that square wave function I got out of that model really surprised me. And then the more I looked at it, the more I realized that the thing that had been frustrating me on multiple other iterations, and I won't embarrass myself by saying how many different iterations I tried on that one, but was almost always that there was diminishing or expanding signal. So the mins and maxes were getting further and further apart as that progressed, and or the phasing was shifting dramatically. Pardon me. But this one, though, if I just looked at only those things, I would have said, well, from here, I can go do something to get it squished down into the sine wave shape now that I got consistency in the minimax and the phasing. But that, again, an idea that I had not considered in sort of my day job or doing some of this sort of modeling work, that sometimes the right answer with a neural network, for example, might not be another neural network. It may be some sort of post-processing signal filter that gets you where you want to go. Okay, and then just sort of final conclusions here. I would definitely advocate that RNN modeling must also include a good understanding of the data that you're working with. Often as data scientists, I think you'll find that you're being thrown data that the person bringing you the problem doesn't fully know or understand either. Nothing can understate the importance of a good exploratory data analysis. But I'd also say, going further, and if it's a business use case or a healthcare use case or scientific use case, trying to gain some understanding of what's going on behind the scenes, there may be some things there that will inform how you design or build the model. And again, the sunspot cycle I would point to. Other thing I think I learned out of this is that simple cycles can in fact be effectively modeled with simple RNNs. As hot a topic as LSTMs and transformers are now, the right tool for the right job certainly comes to mind. And seeing something like the sine wave exercise, I think, was a good reinforcement of that. The other conclusion is that there is some value in running multiple experiments with parameter settings. Don't go just changing and adjusting architecture for the sake of adjusting architecture. I would also encourage you to only change one thing at a time. I initially tried experimenting with 2 or 3 changes at a time and realized the differences. I just had no way of learning anything from that. And so I got a little more disciplined about, okay, keep everything else the same, change the number of neurons. Keep everything else the same, including the neurons, change the parameter length, the input sequence length. So if any data science discipline really calls for good experimentation, I really think neural networks would be one of those. And then finally, I was pleasantly surprised when I found that early stopping function in the Keras data tech stack there. I can only imagine what other capabilities are there that would be good leverage for some of the problems that we've tried. I feel like we've probably learned a lot with what we've got, but certainly one of the conclusions I have is spend a little time in the documentation and you might find some capability that is there that you had no idea is there that could be really useful, like the early stopping. So I don't think my dogs have any questions about the presentation, so I will stop there. Thanks, everyone. I'm looking forward to hearing others' presentation.